Hello, my students, and welcome to another episode of Math at Summit. That's me when I'm like 60. That's me like when I'm a lot older. But welcome. Before we get started with this video, I'm going to go ahead and point out that we hit 20 subscribers. That's right. No more double digits. The dog days are over. 20 subscribers, that's 2 digits, my friend. You know what comes after 2 digits? 3 digits. You know what comes after 3? 4. That's right. That's math, right? 3 comes after 4. You came here to learn some math, and that is exponential growth, my friend. We are becoming viral. We are going viral. So, huge shout out to my 20 subscribers, all 20 of you, right? It's just 20 today, but you look back tomorrow, maybe it's 1,000. I don't know. Exponential growth, that's how it works. So, the first comment on this video, I'm going to go ahead and do a little bit of a celebration. Give out 2 Z-Bucks to the first person to comment on this video, right? And before you know it, everyone's going to want these Z-Bucks. Even people who don't go to Summit, they're going to be watching these videos like, dang it, I didn't get the first comment. Alright, enough with the nonsense. In all honesty, if you think there's too much nonsense in these videos, definitely express your opinion, let me know. I get weird, I get crazy. That's just me having fun while making these videos. I specifically don't include that in the time jumps, in the time links. So it's kind of like a kind of a bonus for everyone else. But if you don't like these things, I can definitely cut it out. It's just me having fun. So without further ado, we're going to talk about some fake stuff. Just kidding. We're going to talk about imaginary numbers. They're definitely not fake. They just have that poor name of imaginary. And we are going to do some thinking on this, and we're going to see what happens when we start raising imaginary numbers to a power. Okay? Now, let it be said, there's a few things we're going to be working on in this video. Do I want to break it up? I don't know if I want to break it up. We'll find out as I go on. But the first topic we're going to talk about is imaginary numbers, right? And specifically looking at what happens when we start raising them to powers. So, the imaginary value I equals the square root of -1, right? I equals square root of -1. This can be used to find higher powers of I. They are I equals the square root of -1, I squared equals -1, I to the power of 3 equals -I, and I to the power of 4 equals I. Right? And let's go ahead and let's make this more than fact. Let's reason our way through this. Let's figure out how to derive these things and see how this actually makes a lot of sense. So, over here, we're going to go ahead and do our thinking about this. So, what do we know I to be? And this is definition based, right? This is saying that when I take the square root of 1, that's when, I went imaginary, right? Mr. Zoyas is at it again. He's gone cuckoo, and he is imagining things. Right? We have imaginary stuff now because we took the square root of -1. Now, what about when I have I squared? Well, let's go ahead and think about this like a mathematician would, just very analytically. Let's break this down. Okay, that was too cringy for me. I just cringed myself out by doing that. Oh god, maybe I should start dropping rhymes in these videos. If you want it, go ahead and say it down in the comments. Maybe I can start busting rhymes in the video. But if you don't, you definitely don't have to unleash that evil on the world. So what we did here, right? Being analytical mathematicians, we just said, hey, I know I is equal to this, and so let me just go ahead and plug that in underneath the square. Right? So we just have the square root of -1 squared. Now you may be looking at this and be like, oh wait, this is easy, right? The square root and the square are inverse operations, so they just cancel. What does that leave us with? -1. Okay, cool, right? That first one makes sense. right? We square it, we get rid of the square root, and so then we just have -1. We came back to our real dimension. Interesting. Weird, but interesting. Right? So, okay, now let's go ahead and look at when we have I to the power of 3. So, okay, we're going to be mathematicians about this again, and we're going to say, hey, let's go ahead and think about it more like I to the power of 2 times just one I, right? I to the power of 1, if you want to call it that. Because that would be equal to I to the power of 3, right? Okay, cool. But what do we know I squared equals? What did we just find out? Right, so this is going to equal -1 times I. Or more simply written, -I. Right, there's the third one. Whoa! That makes a lot of sense. I wouldn't have guessed it, right? When I was awkward in high school with a lot of acne, and in my Algebra 2 class, I wouldn't have guessed that. So now let's go ahead and see what the next one looks like. Right, so this one, we're going to take that same kind of logic, and we're going to break it up into something that's a little more easy to think about. So we can say that this equals I squared times I squared, right? That's just total, we're multiplying 4 i's right there, so it's the same as that. But we just said I squared times I squared. But what do we know each I squared to equal? -1. Right, so -1 times -1. What is -1 times -1? Full circle. Oh, that's the circle of life. I guess the circle of life is kind of full circle, but you get the idea. We just came back to 1. This is what? Right? We had imaginary, real, imaginary, real. That's weird. That's weird, man. You're weirding me out, bro. And go ahead, and I want you to pause the video and predict what you think I to the 5th power will be. Right? We noticed that there's some kind of... We just came back to real 1. Right? Real 1 is like... That is like the most basic number. Right? It multiplies by anything to be itself. We just got back to step A in the real dimension, right? Where we started was 1 times imaginary, right? I know we don't say that, but that's kind of where we started. And so I to the 4th power brought us back to 1. Weird, right? It's absolutely weird. So then where do we think I to the 5th power is going to go? Pause the video, think about it. And then when you come back, we can break this down to I to the 4th power times I, which we know to equal, what's I to the 4th power? We just figured it out. 1 times I, or just I. Just take a second, fathom this. Just let this soak in. What does this mean? What can... Just, huh? Right? We start, like, it goes in a circle. I to the 5th power goes back to just what I equaled. So think about that. Say that we have I to maybe, next in line would be 9. I to the 9th power, well, I could say that, hey, that equals I to the 4th power times I to the 4th power times I, which equals 1 times 1 times I, which just equals I. Right? Absolutely weird. And we're going to go ahead and throw some Z-Bucks out on the line. Some Z-Bucks, if you can come up with an equation that's going to describe which values of I will be equal to each other. Right? How can you describe, or how can you predict which I values will be equal to each other? Which powers of I? Sorry, I should really say powers of I. Okay? Cool. That was a great little dip into theoretical land. Some really interesting and just fascinating concepts over there. So now, but of course, we want to bring them back in. We're going to bring this on home and apply them. Okay? So now we want to simplify these expressions. So we see Now we can call this a binomial, right? It's a binomial, just one of our terms is real, one of our terms is imaginary, times a binomial. So let's go ahead and do this binomial multiplication. Again, box or foil, but I know you want to pick box because foil sucks. And this is the way we're going to do the box. So notice it's the same exact method, right? You know, it's like we almost didn't even notice the I was there. We didn't even flinch when we saw the I, right? Like, oh, like that's 9I. Yeah, we write 9I there. What's I? I don't know. It's just part of the method. If it's there, we write it there. But what is I? I don't know. Just follow the method, right? Like we just stick to the method. The method doesn't change the things we're doing it to do. All right. So doing this multiplication, we're going to have 7 times -4 is -28. 7 times 9 is 63I, right? And that I is multiplying, so it's still going to be there. -3I times -4 is going to be 12I. And then -3I times 9I. That's going to be -27, and then I times I. And I'm just going to first write it out like that, because don't forget we have these two i's that are multiplying. And for right now, I'm going to write I times I. Right? A lot of you may be like at the edge of your seat, it's I squared! It's I squared! Just write the I squared! Hold up, okay? We're going to get there. But for right now, I'm just writing it like that. Okay? And so then, that's going to equal all these things added up. So -28 plus 63I plus 12I minus 27I, and here you go, now you're happy, I squared. Okay? That's what it's equal to. We just did polynomial multiplication the same way we would do any other polynomial multiplication and found out what it equals. Alright? Now, we're almost done, we're close. So A, we want to combine like terms, and then B, we want to use this brand new skill that we just figured out, right? This brand new conclusion that we just came to. So first off, let's go ahead and combine like terms. So what like terms do we see in here? Well, that's real -28. That's imaginary 63. That's imaginary 12. Oh, those are like terms, right? Same variable, same power. In this case, now same dimension. They got to be the same dimension of numbers, both imaginary. So 63 plus 12 is going to be 75. Imaginary, right? Still in the imaginary dimension. Imaginary numbers add with imaginary numbers. Real numbers add with real numbers. And then minus 27I squared. Okay, now we don't combine our I squareds with our i's. They're different terms, right? I is to a different power, so we don't combine it with the I to the first power. Okay, so we're left with -27I squared. Alright? Now we want to use those new rules that we just learned about, right? Hey, what's going on up here? I see you over there. I see you, right? Right, we got I squared. What's I squared equal? -1. Let's go ahead and plug that bad boy in. Say, try this on for size. Minus 27 and I squared times -1. Right? Then simplifying this a step further. Plus 28. Right? We had a I squared. That brought us back into our real dimension. Lo and behold, now we have two real numbers, again, that are like terms, which can combine with each other. -28 plus 28 is going to be 0. We are left with 75I. Imaginary 75. Whoa. Totally weird, dude. Right? Weird, but again, as mathematicians, we trust our logic, we trust our reason, and we trust the conclusions they bring us to. So, now let's go ahead, do all over again, except at a little bit of faster of a speed, because now we got the explanation. So, going ahead and doing the superior method, we are going to do box method to our first polynomial that's multiplying. Right, and I know I just jumped right into this, but make sure you're taking a second to kind of like step back and like see what's going on in this problem. Right, so we have two binomials that are multiplying plus a monomial, right, that's a monomial, just one term, times a binomial. So we're ultimately going to have to multiply polynomials twice. Okay, and then we add together anything that's like about that. So this can now replace all that stuff. So we're going to have, and I'm going to draw an arrow bringing it down to here, 4 plus 8i plus 3i plus 6i. Oh, mistake. You thought you were going to get some Z-Bucks. Not today! Right, that's I squared. Okay, make sure you don't forget that. Make sure you don't do a typo like Mr. Zoyas. Plus, now we want to do this. Now, okay, I'll give, I'll throw the FOIL method fans a bone. This is the one time I'm going to use FOIL method. Right, when I have a monomial times a binomial, sure, whatever. I'll do the cheaper of the two methods. I'll do the uncommon method. I'll do the people's method. The really low one. So, 3i times 4, that's just going to be 12i. Ugh, can't believe I'm doing FOIL method. 3i times negative I, that's going to be negative 3i squared. Cool. Let's go ahead and combine the like terms. I see I squareds right there. 6 minus 3 is just going to be 3i squared. 12i, I, me. 8 plus 3 plus 12. 8 plus 12 is 20, plus 3 is 23. 23i. And 4, and that's it. Our real guy is alone. Our rationalist is alone. We don't have many rational terms in here. Sorry, not rational, but real, right? I was just making a joke that someone who is real is rational. But that's not the case in math, right? Oh, math. Weird, confusing all our definitions. So now let's go ahead and apply that new rule that we learned. What's I squared equal to? Well, that's just a negative. So we have negative 3, 4, plus 23 imaginary. Combining these like terms, sorry, let me write my equal signs right there. Being a very sloppy mathematician right now. 4 minus 3 is 1 plus 23i. Boom. Boom. Shaka, laka, shaka, boom. Cool. Now, on to evaluating imaginary numbers. So, right, this is really just taking the things we learned, right, these up here, and figuring out what's going to happen with it. That's all we're doing with this. Okay, so let's go ahead and do that. Alright? So, we are now just going to evaluate imaginary 3. Right? And so we're going to do this the same way we evaluate anything else. We're just going to take what's in here and plug it in for x. Because, right, after all, that's what it did. It took the place of that x. So, f of 3i is equal to 3i squared plus 3 times 3i minus 9. Calculating that, so we have that square is going to square. That square is going to square our 3 and our I, so we'll have 9i squared plus 3 times 3 is 9i minus 9's. 9! A lot of 9's. I squared is going to equal negative 1, right, because of our new rule, plus 9i minus 9, which will ultimately equal or negative 9s are like terms. So negative 18 plus 9i. Right there. Okay? You know what? We're just going to go ahead and power through this. So we have two more things that we're going to look at. And these really... This next one, so it's nothing new. The language is the newest part about it. So now we're going to look at finding solutions. And to what, you may ask, right? Find the solution to what? We usually see something after there. Find the solution to x, find the solution to y, find the solution to smiley face if that's our variable. But here it doesn't say, and we're going to understand what people mean when they say find the solution. It's common in math to search for the x-intercepts. Remember, when y equals 0, that's our x-intercept, right? X-intercept is going to look like this. Boom, boom. Say maybe like that. So how far do we go on the y-axis? 0, right? X-intercepts when y equals 0 as a solution to a problem. It's common, right? What do we do with things that are common? Oh, sorry. There you go. My little sketch wasn't on the paper. What do we do with things that are common? We take them for granted. We make words out of them. We just take them to be the more truncated version. So thus, these values have become commonly referred to as solutions, zeros, x-intercepts, right, we saw that up there, and roots of an equation. Now, side note, roots only applies to powers of 2 and above, right? When I ask you to find the roots of the equation, that's because I'm talking about when I have to take the root of something, right? The root of something. I only have to take the root when it's a power of 2 or higher. Okay, so roots is just a special way of saying, hey, find the x-intercepts. Right? Zeros is just a special way of saying, hey, find when y equals 0. Right? Solutions is just a really lazy way of saying, hey, find the solution for x when y equals 0. Okay? That's all it means. I ask you to find the solution. If I ask you to find the zeros, if I ask you to find the x-intercepts, if I ask you to find the roots, it's the same dang thing. Right? It's all when y equals 0, and that's how we're going to start off all these problems. Thus, when searching for these values, let y equal 0. Find the roots of y equals this, right? Of equation, right? Roots, when y equals 0. So just like that. And now here, I know this is common. This is very familiar. We've been doing this. This is old news, right? Right, Mr. Zoyas? This is boring. Put something challenging in front of my face. Okay. But the thing is, you're going to be asked questions like this, and if you don't know what the words mean, so side note, I subtracted 16 from both sides because I'm trying to solve for x. Right? I've done this so much, it's just automated. I see a one variable, one equation set up in front of me. I just solve it. That's how it works. Right? When you see this and it says, what is the roots? What is the zeros? What is the x-intercept? What is the solution? It means plug in 0 for y. Okay, then we're going to go ahead and solve this. We'll divide both sides by -1. So we have 16 equals x minus 3 squared. Oh, well, thank you, Mr. Zoyas. You gave us another perfect square to take the square root of. That was very kind of you. You're welcome. So we will have, oh, and don't forget the plus and minus. Plus and minus 4 is equal to x minus 3. We're going to add 3 to both sides. So 3 plus or minus 4 is equal to x. Those are the zeros. Those are the roots. Those are the solutions. Those are the x-intercepts. They're all the same thing. Okay, understand? When you see one of those words, right? I just like, when you see that word, stop thinking, plug in y equals 0. Or just stop thinking, write down y equals 0. Okay? That's what it means. It's just a language to learn right here. That's all we're doing. Alright, and so another way to write this, what's 3 plus 4? Well, that would be 7. Then the 3 minus 4 is -1. Those are both things that x equals. Cool. Find the roots of y equals 3 times quantity x minus 3 squared plus 27. Right? Find the roots. Find the zeros. Find the solutions. Find the x-intercepts. drill it into your head that these are all the same thing, and all we're doing is plugging in 0 for y. Okay? I wish I could be like, oh, here is the good reason for this. Or, we do this because we have basis A and B, and we can pull corollary. I can't say that. We're talking about Toyotas now. We can pull Corolla C from this, and haha. Right? But that's the thing. There's no good reason behind this. This is semantic language. This is the way we write it and the way we talk about it. So, you just need to know it. Right? This is the language that allows us to communicate and then do math. Okay, so now we're going to go ahead and find the roots, which means plug in 0 for y, solve for x. Minus 27, minus 27. Negative 27 equals 3 times x minus 3 squared, divided by 3. Doing that to get rid of the multiplication of 3. Negative 27 divided by 3 is equal to negative 9. Holy smokes, guys, we're going to have an imaginary number. I know that because I'm going to have to take the root of a negative number, plus or minus. Plus or minus imaginary square root of 9 equals x minus 3. Okay, now we're going up here. We're going to cut that out. That's getting annoying. So plus or minus I, we know the square root of 9 is 3, equals x minus 3. Okay, and just basically what I was fast forwarding through that because we know this, right? I know, you know, that we know how to do this. Okay, we are just solving for x, right? We're subtracting 27 from both sides. We're dividing by 3 right here to get rid of the multiplication of 3, taking the square root to get rid of the square, and then just simplifying that square root. Okay, and then we're going to add 3 to both sides. We have plus and minus imaginary 3 plus 3 equals x. Okay, now for all of you out there with low self-control, with very high knee-jerk reactions, right? You may see that, oh, plus and minus 3 plus 3, oh, I know one of my solutions is going to be 0, right? Negative 3 plus 3 is 0. Only if they're real, right? This is imaginary. This is real. We do not mix them. They are different dimensions. Oil and water, okay, do not mix. Alright, so our two solutions are, now let's go ahead and write our real number in front of our imaginary. And side note, that's actually common notation, is to write your real number then your imaginary number. Does not need to be written like that, but it is the way in which these things are most commonly written. So 3 plus imaginary 3, and also 3 minus imaginary 3. Okay? Those are both what x equals. Okay, that was a quick topic, right? Because all we had to do was learn some language. Right? Maybe you learned the language, then you fast forward because you know how to do this. Maybe you skip that part. Good for you. But if you need to watch the video, no shame in it. You're still getting at it. Okay, so now for this last part, so now this is just going to be kind of like building on, it's going to be looking at the flip side of taking the square root, right? So we know that the square root is the opposite of a square. Now let's go ahead and turn that statement around, right? The square root is the opposite of a square, so the square is the opposite of a square root, right? Sounds redundant. Sounds like I'm repeating myself, and funny thing is, a lot of good logic actually sounds that way. Sounds very redundant. But all we're doing is just, we're taking that same statement, we are turning it around, and then using that to solve more problems. So, let's read. The inverse of a square is simply the square root. Thus, solving an equation with a square root simply requires us to square the square root. Square. I don't know, I just said square a lot, so I just wanted to throw another one on there. Solve, okay, so again, wrapping that up, right, we realize that the opposite of a square is a square root, so that means the opposite of a square root must be a square. So let's go ahead and keep that in mind when we're trying to solve equations that now have a square root in them. So solve for x when y equals 3. Y equals the square root of quantity x plus 4 minus 5. Alright, so we're going to plug in, right, when y equals 3, so we're going to go ahead and plug in 3 right here, equals the square root of x plus 4, and again, nothing new here. Side note, I know a lot of you guys have trouble controlling this. Your square root tails go as far as the stuff under the square root goes. If your stuff under the square root stops there, so does your square root tail. Right? I don't draw it over the -5 because that's not under there. Be very clear about that. I know you guys, I don't know if it's poor penmanship or I don't know if it's misconception, but either way, don't do it. And get the back of your hand slapped with a ruler if you do it. I'm just kidding. That's child abuse. We don't do that in here. Okay, so now we're gonna go ahead and do reverse PEMDAS to solve this thing. Right? We know how to solve equations. Nothing new. We're just solving an equation. So we're gonna add 5 to both sides. Brain is working faster than mouth, or faster than hand. Add 5 to both sides, we're going to get 8 equals the square root of x plus 4. Okay? Now write that conclusion. The opposite of a square is a square root. And the opposite of a square root is a square. Well, let's go ahead and undo the square root by squaring both sides. Right? That's all it means, and like for a lot of you, this is like super uneventful. Like it's obvious. It's like, oh well, no, duh. Like it's just the opposite, and you do its opposite because we're solving, right? But understand, like, I guess that's what happens when logic makes sense, and that's what happens. You can get in the flow of logic. Things just make sense, and it's beautiful. It's just absolutely great. It's one of my favorite things about math. Alright, so we go ahead and square both sides. Now realize if that was a -8, still would have been 64. If it was a +8, that still would have been 64. That's both of our solutions coming back into one solution. And so now we are going to have to subtract 4 from both sides. And we will have 60 equals x. And that's our solution. Alright, when x is equal to 60, it's going to give us y equals 3. Just like that. Oakley dokley. So, let's go ahead and go on to example number 2. So, solve for x when y is equal to pi. When for y, well, sorry, let's go ahead and put commas for both of these. So for y equals -1/2 times quantity square root, or square root of the quantity x plus 4 pi minus pi. Okay, same thing. We're going to plug in pi for y equals -1/2 x plus 4 pi and minus pi, right? Outside of the square root, not underneath the square root tail. Mind your tails. Okay, so now we're solving for x. Let's go ahead and begin this reflex-like process of solving for x. We're going to add pi to both sides. We don't even care that it's a pi. We just know we got to get rid of that because it's subtracting, so we go ahead and add to it. 2 pi equals -1/2 square root of x plus 4 pi. And then we're going to multiply both sides by a -2. Because we have -1/2 right there, right? So you can, side note, I guess you can also think about this if it's easier as negative square root of x plus 4 pi divided by 2. You can think of it like that if you want, then it becomes a little bit more clear that you have to multiply. Or you can also just realize that the opposite of multiplying by 1/2 is multiplying by 2. Right? And in this case, the opposite of multiplying by -1/2 is multiplying by -2. Okay, so multiplying both of these sides times -2. I'll write x -2 to show that I'm multiplying by -2. That's not x minus 2, that's times -2. I know the notation gets confusing, especially once you know variables. So -2 times 2, that becomes -4 pi equals the square root of x plus 4 pi. Right? Now, up next is our square root. How do we get rid of that? Is squaring both sides. Okay? So this square is going to go to both parts of it. So we're going to have square root of a negative is just going to be a positive. Square root of 4 is going to be 16. And the square root of pi is going to be just pi squared. And you can actually calculate that if you want. But just, just to have it a little bit easier so we don't have to write this big decimal, we're just going to write pi squared. Okay, keep it easy on ourselves. Okay, so now we have x. The last step before we have x on its own is subtracting by 4 pi from both sides. Okay? So that'll be equal to, well, not equal to, then we'll have 16 pi squared minus 4 pi equals x. Sorry, I know that's getting tiny. That's a pi right there. Okay, and actually I will draw one more arrow going over here. Don't go off the paper. Cool. Right there. Okay, so this is just our final solution to it. 16 pi squared minus 4 pi equals x. Okay? Now, some of you may be asking, wait, why didn't I add those? They both have a pi, right? Isn't 16 pi minus 16 pi squared minus 4 pi equal to 12 pi? Right? And so, to those of you who asked that question, it's a great question, Give yourself a pat on the back. Give yourself some Z-bucks. I don't know how you do that, but just... would it be... So if you were to do that, would it be 12 pi squared? Or would it be just 12 pi? Right? Notice, how do you choose? You have no good reason to choose one over the other. Thus, there is probably something wrong with your assumption. Right? There's probably some bad logic underlying that. Okay? And so the thing is, they're not like terms. One has a pi squared, and the other just has a pi. Right? One's pi squared, the other is just pi. They're not like terms. Keep them separated. Just like that song tells us to do. Cool. Cool, cool, cool.